Well, first of all, welcome everybody to our fourth in the series of our sixth form lectures. And thank you for joining us in record numbers as well, as I mentioned this evening. And thank you also to the West Midlands Chemistry Teachers Centre for making these possible, along with the Royal Society of Chemistry as well. And it gives me great pleasure, immense pleasure this evening to welcome back Sir Professor Martyn Poliakoff from the University of Nottingham. Martyn's research includes gaining insights into fundamental chemistry and also developing environmentally acceptable processes and materials, some of which he's going to touch on today. But he also became very popular and perhaps is even more well known for being the main figure in the YouTube channel, the periodic videos of the elements. As you can probably see from his background, he is an avid collector of all things periodic table and has some fascinating exhibits in his collection as well. I'm sure he will show you some of these as we go through the talk. Just a couple of points. Martyn's talk is a tale of 4 parts, and in keeping with university procedure, where we are told that people can only concentrate for 20 minutes at a time these days, the lecture will be split into 4 parts, roughly 20 minutes. And at the end of each, we will have a session where we will invite questions.
So I'm Martyn. I'm honoured to be virtually in the West Midlands, though I'm actually sitting in the East Midlands. And the title of my talk is The Elements of Chemistry. This is not an original title. Lavoisier, who discoverer of oxygen, invented this title in the 18th century. He had his head cut off on the guillotine, so I hope this won't apply to me as well. And this is my email address. It's easy to find if any of you want to send me an email. So the aim of the lecture is to try and show how chemists like me have quite a strong relationship with a particular element. And I'm going to do this by the 4 parts that Mark mentioned. First of all, getting into a relationship by trying to answer a question, then being drawn into a relationship by making a systematic search, and finally by complete chance. And I'm going to illustrate these points by taking you on a sort of virtual tour around my office at the University of Nottingham. It's quite nostalgic for me. I haven't been there since March. So here's the entrance to my office, and you can see there are quite a few periodic tables, even a periodic table clock. And there are lots of plastic bottles, but I'll tell you about them later. And I'd like to begin by just showing you this periodic table, which was invented or drawn up by EUCHEMS, the European Chemical Society, for the 2019 International Year of the Periodic Table. And it looks rather strange because the area of each element represents the abundance of that element on our planet. It's a logarithmic scale, so the ones that are pretty rarely abundant, like francium, are much bigger, shown much bigger than they really ought to be. And the elements are colored, so those that are green mean that there's an ample supply of those elements on the planet. We're never going to run out of hydrogen. But then those that are yellow are ones which may become scarce in the future. And then the colors sort of go through orange to dark orange, and the dark orange elements are already in quite scarce supply. And there are symbols of smartphones which show the 31 elements that are found in most smartphones. So of course I could cheat and say I've got a smartphone and therefore just holding this up, I've got 31 elements. So I'm in a relationship with all of these. But I have to be honest that even people who love their smartphones rarely love them because of the elements they contain, but just because they're obsessed with messaging and emailing and so on. So incidentally, the human body has only 22 elements in it. So from the point of view of chemistry, smartphones are much more interesting than people. And if you go into any cafe, you can see everybody on their smartphones rather than talking to their friends. And this is clearly because there are more elements in the smartphone than in their friends. So, relating to the elements, the first thing to try and answer a question, and the elements that I was drawn into this case were iron and argon. If you go into my office, one of the first things you'll see inside the door is these boxes. And I teach chemistry, and these boxes contain dog toys. And I often use these dog toys as molecular models. And the particular dog toy I want you to look at is this one here, which I've circled in red. And if you look at it, you can see it here. It has the same shape as this molecule here, iron pentacarbonyl, FeCO5. And there's an iron atom in the middle with carbon here and oxygen, so 5 CO groups. And you can see the same shape here. And this is the iron pentacarbonyl itself, which is a sort of orangey colored liquid. Think about it. You very rarely, or perhaps have never seen a metal compound that is a liquid, but iron pentacarbonyl is. And this molecule was an important part of my doctorate, my PhD, with my supervisor, Jim Turner. And so the question that I was posed by my supervisor, Jim Turner, was what is the shape of FeCO4? What that means is that if you take this compound FeCO5, and which has 5 CO groups, if you remove one of the CO groups, what shape will the remaining part be? Would it be a tetrahedron? Would it be this funny shape here? Or could it be the shape over here? And so the question is, how could you find out? Well, I forgot to show you the dog toy. Here is the dog toy. It's rather good. It squeaks, which sometimes quite excites the students. And the so the way that we studied this reaction was with a very unusual technique called matrix isolation, in which the reactive molecules, because FeCO4 is going to be very reactive. You've removed one of the groups. It's ready to react with something else. So we immobilize them in low temperature solid. And hanging in my office is this picture here. I should say this is a real picture, it's not photoshopped, which demonstrates the principle of the experiment. You imagine here you've got a solid, and embedded in the solid are molecules of FeCO5. And you shine light on it, and carbon monoxide, you can see these currents, will be blown off by the energy of the photons in the light, and the reactive molecule will be left stuck in the solid. Now, you don't use a piece of cake, and if you want to ask me in the questions, you can ask me how you can make a cake with different colored cherries in it. But we did, as the solid, we used solid argon at a temperature of 20 degrees absolute, which is the boiling point of hydrogen, the boiling point of liquid hydrogen, minus 253 Celsius. And in my office, squeezed between some of the things on the floor, there is this hydrogen liquefier that I used as part of my doctorate. It's actually upside down. It should be the other way up, but it doesn't rest on the floor upside down. And this is a picture of the equipment I built at the start, or rather my technician, Maurice Wilkins, built for me at the start of my PhD. And this bit here is over there. So when the experiment was running, it looked something like this. I don't have a photo of the iron compound, but I've got the corresponding chromium compound. So here you can see something at 20 degrees absolute, minus 253 Celsius. And to give you an idea of a scale, this ring is about the size of a ring pull on a can of Coke. And it's surrounded by glass with a vacuum inside so that the water vapor in the air doesn't condense. And in front, there is a window made of calcium fluoride that allows infrared light through. Because if you generate these things in the solid, somehow you've got to find out what they are without taking them out, because if you try and take them out, they'll immediately react. But by looking at the absorption of infrared light, light is absorbed by the vibration of atoms in a molecule. If you're lucky, you can work out the shape. So this is my key result. So here's the infrared spectrum. And the sample that we used had a mixture of the 12 carbon, the normal isotope of carbon, and some of the rare and rather expensive 13 carbon. So we got a mixture of molecules, some with 1, some with 2, some with 3 or 4 13 carbons. And here at the top, what's labeled A, is the spectrum of the absorption of infrared light that I observed. And the question is, what on earth does this mean? And the answer is that you have to calculate what you would expect from different possible shapes. And down here is the shape, what you would expect from a tetrahedral shape. And you can see there are 2 strong peaks and some rather smaller ones that doesn't look anything like the observed picture. But this shape here, which you can see over here with the bond angles 140 and 120 degrees, 145, 120 degrees, gives a pattern that's pretty similar. You can see you even get a big one with a small one here, and then some strong peaks here. And the dotted ones are due to the starting material that's not been destroyed. So we can ignore those. So I answered the question, the shape of FeCO5, you can see is here, which has this very unusual shape. And what that means is that when you remove that group, the bond angle closes a bit, and so you're left with something that looks like a slightly distorted fragment of the starting material. And you may say, well, isn't that pretty obvious? And the answer is yes, when you know the answer. But before I did those experiments, theories predicted that it would have a completely different shape. So in fact, I became quite famous for doing these experiments. So we will now stop sharing the screen. And so I don't know if you can see me here. what I was saying is that if you remove this group, you then get the this shape. So, time for some questions.
So we do have a few already, which is good.
Yeah.
So the first question we have is how do you remove the carbonyl group from the FeCO5? How do you remove it?
Well, the FeCO5 absorbs UV light. The energy of the photon of UV light is more than the strength of the iron carbon bond. So if the molecule absorbs the light, you break one of the iron carbon bonds.
Excellent, thank you. And the other one we have is the only way of finding the molecular shape of the molecule. So how do you find the molecular shape of the molecule? What technique might you use?
Well, at the time I did this experiment, the only way was to use infrared light. But there are lots of different techniques that chemists use for finding structures. If you've got a crystal of the molecule, you can use diffraction of X-rays. And I'm sure there's a diffractometer in Birmingham, and we've got several in Nottingham. If the molecule is in the gas phase, you can use a variety of techniques. The absorption of microwaves is often very sensitive. This is how people recently believe that they have observed phosphine pH 3 on the planet Venus. You can also use diffraction of electrons, which was what about 30 years after I did the first experiments with FeCO4, it was observed in the gas phase using electron diffraction. So, any other questions?
Yes. So how would the shape change if you had different numbers of CO groups?
Well, you can. The answer is that with the right sort of experiment, you can do it a bit like the children's game where they take a daisy and remove the petals, saying she loves me not, and so on. And so you can remove the CO groups. And in the case of FeCO3, if you have only 3 CO groups, I've got another dog toy here. So you just ignore my hand. But the FeCO3 is a sort of, has the iron here with the 3 CO groups hanging downwards. And I'm not sure if anybody has worked out the shape of FeCO2. And FeCO will just be a linear molecule with the 3 atoms in a row. They're very good questions.
Excellent, thank you. I think there's one final one here saying, please could you explain a little bit further as to how the molecular shape of a molecule can be observed using diffractions of electrons or using infrared, etc. So perhaps just a little bit more detail there.
Well, I think the answer is that the principles are completely different from the different techniques. With the infrared, you can relate the number of bands to the shape of the molecule using a mathematical approach called group theory. It's not very complicated mathematics. We teach it in our second year, and possibly Birmingham, they teach it to first year students, I don't know. But so you can predict what the infrared spectrum of a molecule should look like. You can, with the diffraction, is rather like, very conveniently, I have the right sort of visual aid. This is a rather old CD, which I use as a coffee mat. But if you shine light on a CD, you can see a sort of mirror, rainbow, which is caused by diffraction of light. And if you use X-rays shining on a crystal, the crystals diffract the light, the regular arrangement of atoms, and you can detect that pattern And by using much more complicated mathematics than you need to do for a infrared spectrum, you can work out what the arrangement of the atoms are in the molecule. And you can use it for really complicated molecules like proteins and hemoglobin and all sorts of very big biological molecules. So, shall we continue? Okay, we now come to the second thing, which is me being drawn into a relationship with the element hydrogen, but we're going via xenon, which is an element, and carbon dioxide. And I know carbon dioxide is not an element, but it's important for the story. So we had the start of the thing was that some of the compounds, not FeCO4, but other compounds we made were rather more stable than we expected, and we wanted to see them in solution. But since we still wanted to detect them by infrared, we needed solvents that are transparent to infrared. But because infrared light is absorbed by the vibrations of bonds between atoms, the molecules in the solution, in the solvent, will absorb nearly all the infrared light, and you may not be able to see what's dissolved. So we needed a solvent that did not absorb infrared light. And argon, krypton, and xenon are really unusual because they have only a single atom in the molecule, so they cannot vibrate. So they don't absorb infrared light. So we decided to work in liquefied noble gases. And on my bookshelf, there is a picture of a report of the Science and Engineering Research Council. And on the front cover is a picture of my then student, Rita Rapmasis, with a cell for liquid xenon. And over here is a picture of a cell with liquid xenon inside it. You're really lucky. Not many people have ever seen liquid xenon. I think probably your teachers who are watching have never seen liquid xenon. It's a slightly boring, colorless liquid, but it's a dream for infrared spectroscopy. This strange thing here is a shaft that goes round and round to drive a magnetic stirrer, so you can stir up the solution. And in my office, in a cupboard, there is the actual cell for use with liquid xenon. You can see it's getting a bit dusty. And what I want you to see is that there are some very big bolts here, which are needed to hold on the windows to the cell to withstand the pressure inside. And the reason why you need pressure is because argon, krypton, and xenon have a very short liquid range. That is, the temperature difference between their melting point and boiling point is very small, perhaps 4 or 5 degrees centigrade. And therefore, you need to increase the pressure so that you can extend the liquid range. You know that when you increase pressure, the boiling point goes up. In fact, by the time you get to 20 atmospheres, the liquid range of the 3 noble gases overlap. So you can have solvents going from minus 180 centigrade right up to over higher than minus 40 degrees. So it's quite a big temperature range. But what happens if you go to higher temperatures? And you can see this on what is called a phase diagram. You've got pressure on this axis, temperature on that axis, and you've got solid here, liquid there, and gas here. And these are the boundaries in between them. This is the so-called triple point. And as you heat something, the gas and the liquid, if it's in a closed cell, will stay in equilibrium. But when you get to this critical point, the line stops and something quite interesting happens. So let me show you here. If you have a closed cell containing the liquid and the gas above it, and you start heating it, it begins slowly to boil. You can see bubbles, but because it's closed, the vapor can't get out. So the gas gets denser and the liquid is being warmed, so it expands, and eventually the density gets the same and the line between them disappears. And this is what's called a supercritical fluid. And if you cool it down, suddenly there is a storm and they separate back into the liquid and the gas. And I think this is really beautiful. And I used to keep the apparatus for this in my office. And if somebody said they were interested in working in our research group, I would show them this. And if they went, wow, I knew they were a suitable person to work with us. If they looked bored, I suggested they should go and work with Professor X or Y down the corridor. Just on the outer wall of my office, that's the in the lobby, there is this photograph here, which shows the original model for the phase behavior of carbon dioxide that was made for Thomas Andrews, who discovered, or was the first person to describe, the critical point. And so supercritical fluids are highly compressed gases, carbon dioxide or steam, high pressure water vapor, which can be used as solvents for chemical reactions. And when I first learned about supercritical fluids, I fell in love. And this is my first student, Steve Howdell, who worked on supercritical fluids. And here you can see the cell we built for it. Steve is now a senior professor at Nottingham and head of the School of Chemistry and my boss. So my student has become my boss. And what Steve and I discovered as part of his doctorate, or realized, is that supercritical fluids could be really useful for reactions involving hydrogen. Hydrogen gas is not very soluble in most liquids. So if you want to do a reaction between hydrogen gas and something dissolved in the liquid, you have to stir really hard to get the hydrogen into the liquid. But a supercritical fluid is a compressed gas, so it mixes completely with hydrogen. So you can get a much higher concentration of hydrogen in the supercritical fluid. And this slide, when I first drew it, was drawn for young school children, primary school children. So it was colored, so blue and yellow, when they mix, go green, just to show how well they mix. So Steve and I used this high solubility of hydrogen to react a manganese compound, also with carbon monoxide, and this strange ring of 5 carbon atoms. And we reacted with hydrogen with light. H nu means that we use light in supercritical xenon. And we saw the first spectrum of this compound here, in which H2 was bonded to manganese. And we were really excited. This was the first time anybody has observed a dihydrogen compound of manganese. And it turned out that this was really stable and would last for some hours in our supercritical fluid at room temperature. So because chemists are meant to make and isolate new molecules, I wanted to try and make more of this. But first of all, xenon is a fantastically expensive gas. And secondly, you can't build a really big cell to make this in because there are all sorts of engineering complications. So instead, we decided to scale up. That's increased our production by using a flow system. And we had to switch from xenon, which is very good for spectroscopy, to carbon dioxide, which is much cheaper. So we had hydrogen carbon dioxide that we mixed at high pressure, and then we passed it through a reservoir that contained the reactant, the manganese compound. We then had a spectrometer to measure the concentration of hydrogen, then UV light to make the compound, then infrared light to check that we'd made the compound we wanted. And then here where it says V, we had a valve and released the pressure, and the product would be deposited as the gas expanded as a solid. And the compound was expected to be much more stable as a solid than it would be in solution. So we hoped we would get enough to see. And this was the work of my student, James Bannister. And here, this photograph shows a sample of this manganese compound, this rather miserable amount of yellow stuff here. So you can say, why am I showing you this photo? And the answer is, I'm a really bad chemist. I've hardly ever made enough of a new compound to see. And in this case, we isolated a compound that nobody had ever made before as a solid. And I was really excited. And you can see this was in the mid-1990s. And then just at that time, my research changed completely. Instead of making molecules that are of fundamental interest like FeCO4, but completely useless, I switched to the field of green chemistry. Now, green chemistry, as Mark mentioned at the beginning, though I'm not sure whether he used the word green chemistry, involves inventing cleaner approaches to making chemicals and materials. And I'm now really very heavily into this, and I teach green chemistry to all 4 years of our students at Nottingham. And the idea of green chemistry is to develop something in the lab which is cleaner, and then transfer that into industry so industry can start making chemicals more cleanly. And the particular area that I became involved with is trying to use cleaner solvents that are more environmentally acceptable than the solvents that are traditionally used in the chemical industry. And the thing that really got me started in this area was that there was an article in the journal New Scientist in 1994 by an author called David Bradley, which talked all about supercritical fluids, and a bit of it was about our research. I must say I was slightly disappointed by this article because I didn't think it did justice to the wonderful research that I thought we were doing it. But it turned out that this article was one of the most important things that ever happened in my scientific career, because this gentleman here, Thomas Swan, read the article, and he was, sadly he's now died, owner of a company called Thomas Swan & Co., which was the second largest private chemical company in the UK. And he phoned me quite late at night, sort of 9:30 at night, in fact, in this room, and said he'd read the article, he was really excited by our research, and he wanted to collaborate. And that completely changed my research direction, because we decided to work together on continuous supercritical hydrogenation. Hydrogenation is adding hydrogen to organic compounds. So we built an apparatus in which we take the substrate, the molecule you want to react, and hydrogen, and supercritical CO2, and literally mix them together, pass them through a tube containing catalyst. The catalyst turns the substrate and hydrogen into the product, which then flows out, and here you release the pressure, the product goes that way, carbon dioxide goes the other way. And this is my then postdoc, Pete Licence, who is now also a professor at Nottingham, with the apparatus. The mixer is here, the reactor is here, and the product flows out at the bottom. So I've got a reactor here, so I shall switch on the light to give a bit more. So you can see this is the reactor, which is just a metal tube, somewhat smaller than my hand. And just to show you it's a tube, you can put a pencil right through and take it through. But normally, if you're doing a reaction, it contains a powdered catalyst. And so our experiments were a success, and we built a full-sized plant. So you can see here is a worker, and here is the reactor. So he acts as a convenient scale for the reactor. And this was the world's first continuously operating supercritical chemical manufacturing plant, and it opened 18 years ago in July 2002. And this is a bottle of the first product. The reaction we did was the hydrogenation of this molecule here, which is called isophorone, which can be made from acetone, propanone, and you add hydrogen across this double bond to make a single bond. And the product has a very unromantic name. It's called trimethyl cyclohexanone, TMCH, and it is used as a solvent for things like perfumes and fragrances. And you can see the bottles has on the label, batch 1. I was really excited. You probably don't realize that chemistry professors at university normally do not build chemical plants. And so I sat all morning looking at this bottle and thinking how wonderful it was. And then one of my students came and said he needed it, and I haven't seen the bottle again. So on the wall of my office is the invitation to the grand opening of the chemical plant. And you can see it's been there so long on the wall that my name has almost completely been bleached by the sunlight. And here's a picture of the grand opening. Here's Tom Swan, Lord Sainsbury, the Minister of Science. And this is Pete Licence. And here they're watching the demonstration of the supercritical fluid that you've just seen on video. And this, I was so excited that my long-suffering wife was taken to see the plant. Here you can see Janet wearing a hard hat. And my student Fiona got a job at the company, and here they are standing in front of the plant. And it was really good for the company. This small UK company was listed in a prestigious American journal, Chemical Specialties, as being one of the top 20 innovative companies, chemical companies in the world. And they're quite famous companies like 3M and Lubrizol and companies like that that you have probably heard of. And also I and my Steve Howdell and my colleague Mike George demonstrated these supercritical fluids at the Royal Society Summer Exhibition, which takes place in London every year. And I would encourage you to go to the exhibition because it's probably the best science exhibition in the UK that there is. So we now come to the second lot of questions. Mark, over to you.
Certainly. Well, we do have a few more questions. Starting with your supercritical fluid, actually. Someone is asking, first of all, what happens at the critical point? So maybe why that meniscus disappears.
Well, the reason why the meniscus disappears is because the density of the liquid and the density of the gas become identical and you cannot distinguish between them. Because the only reason that you can see the difference between a gas and a liquid is because they have different properties, different densities, different refractive indices.
Excellent, thank you. And then someone else asked, how would the phase diagram differ between different noble gases?
The phase diagram will be essentially the same for most substances, even for water, though the lower part of the phase diagram for water is slightly different. But for pure substances, the phase diagram will look much the same. Sometimes compounds like ethanoic acid, acetic acid, decompose below their critical point. But by and large, the phase diagram for pure substances all look the same. When you get mixtures of substances, it gets much more complicated.
I've got a question here as well. What makes a solvent a clean solvent? What is it that we're looking for?
Well, you could perhaps ask what makes a dirty or an environmentally less acceptable solvent. The question is, would you be prepared for that solvent to be released into the environment? Now, carbon dioxide is completely harmless from the point of view of the environment. Of course, there's the question of global warming, but it doesn't cause any harm. And in fact, probably several of the people watching are at this moment drinking fizzy drinks, which have carbon dioxide in it, and they're fine. I should say that our process didn't generate carbon dioxide, but was using some carbon dioxide that somebody else had made, so that it wasn't actually adding to global warming in that sense. And the CO2 was anyway largely recycled in the plant. More questions?
Excellent. Actually, a nice bit of general advice here. You mentioned your research students. Someone's asked here, what advice would you give to someone wanting to go into research in chemistry when they are older?
Well, if you want to do research in chemistry, it's really quite important to do a doctorate. I got an email just before this lecture from the mother of a 10-year-old child in Kalamazoo saying that her son was desperate to do a PhD in chemistry. But I think what I would say is that, and as you will see from this lecture, the areas of chemistry that I have worked in have changed quite substantially during my career. I'm perhaps unusual because I think the range of areas that I've worked in has been rather broader than many chemists do. But what you have to do is to do a doctorate which trains you how to solve problems in chemistry. And then you can apply those skills to all sorts of problems. And at the moment, we are at a really important time because society is facing enormous challenges of sustainability. And by sustainability, I mean carrying out chemistry in a way that can carry on for many generations, for your children, for your grandchildren, your great-grandchildren. You cannot base the chemistry on oil because oil is going to run out. So, and it is young people like you who've got to have the ideas how we can solve these problems. I'm already getting a bit old to do this, and even Mark's a bit old. So you've got to, it's the younger generation who've really got to go in. And it's a very exciting time because you can do something that's very useful. And if you don't succeed, humanity is doomed. So that's not a very cheerful point to end. Is there another more cheerful question, or shall I go on?
So
I have a couple as well.
So sorry, yeah, over to you, Steve.
Okay. First of all, what were you hydrogenating, if we're allowed to ask?
I mentioned this molecule isoferrone, but we did hydrogenate some other compounds as well.
And following that, did the use of continuous supercritical hydrogenation increase the yield compared to doing it without that method?
The answer is that it was much easier to control the reaction. So the product came out completely pure, and apart from a small amount of carbon dioxide dissolved in it, so it had to be allowed to vent, but then the product could be sold without any further purification. Whereas the traditional routes to hydrogenate isoferrone requires quite a costly separation to remove different products and get out the one you want.
I've got one more student question. Dr. Reed, I don't know if you have any as well. Dennis asks, if past the critical point, the gas reaches the density of the liquid, why doesn't it become liquid?
I think if you think about it, the reason that a liquid is a liquid is because there are quite significant positive interactions between the molecules that stops them flying apart in the way that the molecules of gas do. If you open a bottle of milk, the milk doesn't shoot out of the top because it has the liquid. I know milk is not a pure liquid, but you have significant forces between the molecules. As you heat up the liquid through the critical point, those forces between the molecules get less compared to the thermal energy of the molecules. So you can force them together to a high density, but their interaction is essentially becomes more repulsive. So if you release the pressure, they fly apart. It's a really good question, Dennis. Okay.
Thank you. Yeah, in the interest of time, should we continue?
Yes, we now have making a systematic search for the elements with cobalt, copper, nitrogen, and bromine. I don't know if you can see. I have quite a fine bromine here on my tie, especially for you. So the starting point from this is my office. Again, well, in my collection of plastic bottles. This is just some of the plastic bottles. The office is full of plastic bottles, and my secretary, when I had one, was in despair, and now they're more than when she left. And my latest bottle here, I got in the Great Hall of the People in Beijing in January. And the reason why I'm interested in these bottles is to be found if you look at the bottom of the bottle. And if you look on the bottom, they have this recycling symbol and underneath PET, and T stands for terephthalate, which means they're derived from this molecule here, which is called terephthalic acid, which is benzene with 2 acid groups in the para position. And terephthalic acid, which in the trade is called TA, is made from dimethylbenzene, which is called paraxylene, and it is reacted with oxygen at quite a high temperature in solvent, ethanoic acid, acetic acid, with a catalyst of manganese, cobalt, acetate, and bromide. And a typical TA plant will make somewhere between 500,000 and 1 million tons a year. 1 million tons is approaching 3,000 tons a day. So it's a really big plant. And terephthalic acid plants are very energy intensive. You have to put a lot of energy in. But the main problem is that the product, TA, is insoluble in the ethanoic acid, and it precipitates. And it precipitates in a slightly impure form. And half of this huge chemical plant is needed to purify the TA. And if you don't purify it, you can't make the PET plastic that people want for plastic bottles or for polyester shirts. So we wondered whether we could use supercritical water. Now, water becomes supercritical at 374 degrees centigrade and a pressure of 218 atmospheres. So that's quite a high pressure. But as you probably all learnt, water molecules in water are hydrogen bonded. But as you heat it up, those hydrogen bonds become weaker. And by about 300 degrees centigrade, water has similar solvent properties to acetone, propanone. And therefore, it starts to be able to dissolve organic molecules. And when you go through the critical point, oxygen is completely miscible. So we wondered, because you can dissolve organic compounds, including terephthalic acid, and oxygen is miscible, could we use supercritical water to make terephthalic acid? So the idea is that we would take the xylene, oxygen, and a catalyst in supercritical water above 374 degrees centigrade. And this would be a really nice reaction because you would make the product TA and the byproduct is water. So the water would just add to the solvent and it wouldn't cause any problems. So you'd have no organic solvents and a homogeneous reaction. That's everything is dissolved into the solvent. But there's a slight problem, or 2 problems in fact. What you've got to do is to take very hot steam and oxygen and mix them with an organic molecule, paraxylene, which is flammable, and a catalyst in cold water, and you've got to mix them together without getting an explosion, and then with luck you'll get the product. So the 2 questions are how to mix them safely and which catalyst to use. So on the table in my office, among all the other junk, is this reactor here, which has a heater up here and some tubes at the bottom, which is one of the reactors we used for doing the xylene reaction. And if you look at it over here, one of my students forgot to put in the thermocouple that controlled the temperature, and it just got hotter and hotter, and the aluminium, which melts around about 650 degrees centigrade, melted and ran down and made this rather artistic arrangement. So I keep it on my desk or table in my office just to warn students to be careful, and at these high temperatures things can go wrong. And this is the first version of our apparatus. Here you can see the pumps to pump things in, all sorts of safety locks. Here's the oxygen compressor, the reactors are here, and the product comes out in solution there. And this is Eleni Vanadou, who was my student at that time, who was doing the experiments. And we had to optimize the catalyst, try and find the best catalyst. And nobody before had done catalytic reactions in this way in supercritical water. So we went moderately systematically right across the periodic table and a bit down as well, even got as far as bismuth. And in the end, we found the best catalyst was a mixture of cobalt, copper, and ammonium. I know ammonium is not an element, but it's nitrogen, and bromide. And that catalyst worked really well. And you can see these are samples from various stages of the optimization. To begin with, it came out looking rather like a healthy breakfast cereal, all bran or something like that. And gradually, as we improved the selectivity of the reaction, got it to make just the product we wanted, you can see it got whiter and whiter. And the TA that came out in the end did not have the impurities that one has in the normal process that's done industrially. And this was an enormous project. It ran for 23 years from 1995 when we started to 2018, it was 2 years ago. And all these people in green are those who worked at Nottingham on the project. And down here are the ones who worked with our industrial collaborators. The industrial collaboration began with a company called ICI. And although the people stayed the same, the company changed its name 5 times during this period and ended up called Invista Performance Technologies. And I've highlighted 2 people who's in orange, Duncan Housley here, who was working or still works at Invista and who did his doctorate part-time with me in Nottingham while working in the company. And the other one is Ed Lester, who at the start of the project was a young academic at Nottingham in chemical engineering, is now a professor. And Ed took the reactions of some of the metal salts that we were using in water and has founded his own company, which is now operating in Nottingham. It's called Promethean Particles. And this is the world's largest continuous manufacturing of nanoparticles. These are very small particles of metals and metal oxides. And if you like, this span out of our supercritical water experiments trying to make TA. So, Mark, I shall stop again and we will have the next bout of questions.
Okay, so we had a couple. First one is interesting. You mentioned the catalyst that you used. The question is, what method was used to find the best catalyst and the composition of the catalyst? Did you just go along a period, a group, or what was the method that was used?
Well, it was known that we needed a halogen, so we focused mostly on bromide. And we began with manganese bromide because that's the traditional catalyst, and then systematically just tried one element after another. Some of them, like sodium bromide, didn't give any results at all, which I suppose is not surprising because you really need a transition metal that has different oxidation states. And just we worked moderately systematically through the periodic table. Sometimes it just happened to be whatever compounds we could find. I think somebody in another lab had lanthanum, so we tried that.
Excellent, thank you. And again, people impressed by your range of plastic bottles and very fascinated by the fact that under certain conditions, water may be able to dissolve them. Again, a question relating back to supercritical. Someone asking, what does supercritical mean in relation to water? So what exactly is water in a supercritical state?
It is, well, it's essentially highly compressed H2O gas. And the supercritical steam is used quite widely in power stations. All the most efficient thermal power stations now operate with supercritical steam because they are at much, the higher the temperature you can operate, the larger proportion of the heat you can turn into electricity.
Great. Got a few questions here as well.
Yeah.
From Anushka, who's keen to say that she's a massive fan of the periodic videos as well.
Thank you, Anushka.
Anushka asks, how are the properties of supercritical fluids? How do they differ from those of typical liquids or gases? And what are the applications, perhaps other than solvation, that you've mentioned, if any?
Well, the answer is that supercritical fluids, they differ from liquids in that you've got to keep them in a sealed container or they just expand. They differ from gases in that most of the gases we are familiar with obey the gas laws, like Boyle's law, that if you double the pressure, you halve the volume. Supercritical fluids are very non-ideal gases. If you increase the pressure, their volume will decrease more than you would expect. And their main difference is that you can dissolve liquids and liquids and solids, not all liquids and solids, in a supercritical fluid, and which you can't do normally with a gas.
Have another one.
Yeah.
Does the reaction using supercritical water cause any environmental harm?
Well, we've only done it on a small scale. In principle, you might think that water is a perfect solvent for doing reactions in because you can just let it run away. The problem is that if you use organic chemicals with water, you will contaminate the water and you have to clean up that water to get rid of any trace organic compounds. But it is not too bad.
Another one.
Yes.
Is there any way we might find supercritical fluids in nature? I think outside of the lab.
Yeah, you will find them. You've probably seen on some of the more adventurous underwater programs on television, what are called black smokers, which are volcanic outlets at the bottom of the sea, where the pressure is very high because they're very deep in the ocean, and the water coming out of the those vents will be supercritical. And in fact, supercritical water is very important in geology, and a lot of minerals are deposited because the precursor salts have dissolved in superheated water or supercritical water. However, I've never been down to the depths to black smokers, so I've never seen them apart from on television.
If you don't mind, I've got one question of my own as well.
Yeah.
I'm quite surprised that xylene, being a hydrocarbon, dissolves in any form of H2O. Obviously, a very polar supercritical. Why?
Yes,
Why
I mean it's because the hydrogen bonds, get weaker as you raise the temperature, and quite a large number of organic compounds will dissolve in high temperature water. And in fact, terephthalic acid, which is an absolute beast to try and dissolve, it doesn't dissolve with many organic solvents at room temperature, dissolves in water above 200 degrees centigrade. And in fact, the current plants purify terephthalic acid using water at 200 degrees centigrade. But for goodness sake, don't try and do this at school because the pressures are too high.
Sounds like sage advice. Just a final question here. There must be some quite significant engineering challenges when you sort of scale up supercritical from the lab to an industrial process. Is there a limit on the sort of size of an industrial supercritical cell?
The answer is yes, but you may realize that in 5 years' time, we will be celebrating the 200th anniversary of the first commercial passenger steam train in the UK, going from Stockton to Darlington. So there is a lot of engineering experience in our country of using high pressure steam for steam engines. And also many types of nuclear reactors involve high pressure steam as well. So there are engineering issues, there are questions of materials, but this is something that is relatively well understood compared to some other engineering issues. Okay, shall I do the last bit?
Yes, certainly. Thank you very much for answering those questions.
We come to the last bit, which is by complete chance. And the element is niobium. So 9 years ago, I was elected the so-called Foreign Secretary and Vice President of the Royal Society. This is not the Royal Society of Chemistry. There are many organizations in the UK called the Royal Society, and there's only one that people just call the Royal Society, which is the UK Commonwealth Academy of Sciences. And it was founded in 1660 when Charles II came to the throne. And the Foreign Secretary's role, as defined in 1663, is to enjoy mutual intelligence and affairs with all manners of strangers and foreigners. So I spent 5 years doing that. And in effect, what it is was to be a sort of ambassador for UK science, traveling all over the world, but also being involved in things at the Royal Society. And in 2013, there was an exhibition held at the Royal Society called Romantic Chemistry. This is not romantic in the sense of love, but the beginning of the 19th century was the time of the Romantic poets and so on. And this exhibition was sponsored by a Brazilian mining company called CBMM. And CBMM is the world's largest producer of the element niobium. And at the opening of the exhibition, I was asked to give a talk on the chemistry of niobium. And as Foreign Secretary, I couldn't refuse, but I knew absolutely nothing about the chemistry of niobium. But a miracle happened. I was corresponding with a Chinese student who was hoping to come and do research with me. And he had an email address similar to niobium34@gmail. This is not the actual email address, so there's no point trying to email him. And so I asked him whether he knew any interesting things about niobium and got a long email back, which saved me. So he gave me these facts, and the talk was a huge success. And I had a huge surprise because the representatives of CBMM, when I explained about the student, offered to pay for his PhD with me. Now, it turned out that in the end, he took a PhD with somebody else, but CBMM still decided to pay for a student to work with me. And the idea of the project was that niobium phosphate, which you can see here, which is a white powder, is a solid acid which is nearly as strong as sulfuric acid, which is really surprising. It looks quite innocent, but it's a very strong acid. So we wondered whether niobium phosphate could be used as a greener acid catalyst. And it turned out that it could be. With my colleague Mike George, the one you saw in the photo, and my student Jing Jin, or our joint student Jing Jin, we published a whole series of papers, and one of them we got our article on the cover of the journal, and you can see here there is niobium phosphate with a key step in the reaction. And then I was invited with Jing Jin to visit the mine in Brazil, and the CBMM mine in a place called Araxá, which is 7.5 hours drive from Sao Paulo. And you can see here's Jing Jin and me. They wanted me to look funny, so I wore a hard hat. And I was amazed. I assumed, coming from Nottingham, which used to be a coal mining area, that the mine would look black and dirty, but you can see it looked very green. They even had a zoo there. And in my office on the side, there is a sample here of the ore which they dig out of the ground. It's a huge open cast mine. And I was given, though I haven't won, a medal named after Charles Hatchett, who was the discoverer of the element niobium. And next to this sample of ore are these pieces here, which are a mixture of iron and niobium, which is called ferroniobium. And ferroniobium is really important in the manufacturing of cars. And at the mine, they had this really colorful car showing with the different color codings, the different levels of niobium they had in the steel and the different parts of the car. As you know, cars are designed to have crumple zones, which will absorb crashes and so on. And you also need bits that are very strong. And the point about niobium, and when I'm finished, I will demonstrate to you why this is, niobium can strengthen steel so that you don't need to use so much steel to make your car. So 200 grams of niobium in a car like this will save 100 kilos of weight. And if you think about that in the lifetime of a car, it's like saving the weight of a heavy passenger on every journey you make. So you save a lot of fuel consumption. So in this booklet, which I've got here, which was the booklet of the exhibition, because I was Foreign Secretary, I was asked to write an introduction. And so my introduction said Long before today's mass media, they, the chemists who talk to the public, were almost stars, as witnessed, for example, by the popularity of Davies' lectures at the Royal Institution. The first one-way street in the world was in London in Albemarle Street, because so many people queued to hear Humphrey Davies' lecture in their carriages. And it's sad that so many modern scientists are shy of performing to the general public. Communicating with the public is part of our scientific heritage, not an activity always to be delegated conveniently to professional communicators. But then I went on at the end. At the same time, modern scientists must be humble. They sometimes do not understand social media and can come across as pompous or boring. So I've been very lucky to have been able to collaborate with Brady Harron, who's a very talented video journalist, who's shown me how one can communicate science in a way that I hope is neither pompous nor boring. So I've come to the end. I want to thank all the people who guided me when I was young, my students, co-workers, colleagues, and collaborators, particularly my colleague Mike George and my former student Steve Howdle, and Jim Turner, my PhD supervisor, who still lives in Nottingham, and we see each other quite frequently, and everybody who funded my research. And I'd particularly like to thank Rich Wilson, Rich Meehan, and Mark Geiler, who are some of the technicians who support our research. And it's really important for you to realize, even in your schools and colleges, technicians are a vital part of the scientific enterprise. And I would particularly like to thank our technician, Neil Barnes, who has worked with me for 12 years doing demonstrations for our videos. So I will end up to show you the badge that I usually wear. I haven't got one here at home, which says, "I love technicians." Thank you. We now have a few more questions.
Excellent. Well, thank you very much, Martyn. Before Jill gives a kind of vote of thanks, there are a few more questions coming in.
And I need to do my demonstration. But...
Oh, yes, we'll let you do that first.
Okay. So I need to, when I gave this lecture in February, I had an old £20 note, but now unfortunately they're all plastic, so I can't do this with a £20 note. This is an experiment you can do yourself. It's quite safe. If you take a piece of paper, you can pull it really hard and you won't damage it. But if you make a small tear and then pull, it immediately comes apart. And the steel that makes up cars is not a single piece of metal, but consists of grains. And the boundaries between those grains are a weakness. And that's why the cars, if you have an accident, can crumple. But if you, so I've got some sellotape. Well, this is brown tape because it's easier for you to see on video. If you make a tear and then put a piece of tape across the bottom of the tear, can you all see that? If you pull, it now doesn't break. And if you mix a little niobium in the steel, it accumulates the niobium along the grain boundaries and stops cracks propagating, so that if you do have a bang, the steel doesn't break. Over to you, Mark.
Excellent. Well, thank you very much for that great demonstration as well. It's fascinating.
It's even better with a £20 note, because the audience, when it comes in half, the audience gets very excited.
I can imagine. Yes. No, thank you for that. Yes, there are a few questions coming in. You mentioned your periodic videos, which everyone knows and is wonderful. Interesting. Someone has asked, what has been your favourite periodic video to make? Do you have a favourite?
Well, I actually have. We did, to celebrate our 10th anniversary. I selected 10 videos. I suppose. To begin with, it was the video about the element hassium, where I was filmed. I didn't realize that I was being filmed, saying, "I know nothing about hassium, shall we make something up?" And that was the opening of the video. I suppose that one of my favorite videos now is about the one that was made by Brady and me in Moscow about the naming of the 4 elements: nihonium, moscovium, tennessine, and aganeson. And I was invited to lecture at the naming ceremony. I was terrified. I had to lecture in Russian, and but it was good for me. And also, I suppose I like very much the video we made for the opening of the International Year of the Periodic Table. But I do enjoy looking at some of the old experiments, because I've forgotten some of them, and they're really great fun.
Excellent, thank you. Someone has asked how accessible, how easy is it to obtain niobium?
Niobium, I think, is quite easy. Well, buy a car as a start. But I think it's not a terribly expensive element. And apparently this hole that we saw in Arashar contains, at the present rate of using niobium, contains 600 years supply. So it is a relatively abundant element compared to some.
Excellent. I mean, it's often fascinating just what a large effect a very small concentration of a metal in an alloy can have. And I know in jet engines, is it rhenium that's added, and it really increases the melting point of the engine. So
yes, this is for the turbine blades in the jet engine.
Yeah.
They're really interesting. The turbine blades, at least the smallest ones, where it's hottest, are single crystals of metal. And I have one in my office, and if we were there, I could show you, but it's not very big. And that is rhenium. It's quite interesting that rhenium was only discovered in the 1920s. And I've got books here with periodic tables that don't have rhenium on them.
Wow, amazing.
A few more questions here if we still have time.
Yes.
Yep.
Okay. So another message from Dennis, who asked the question earlier as well.
Yes.
He says, surely you could also find supercritical fluids in Jupiter. I read that it's thought you can find solid metallic hydrogen at the center, presumably surrounded by seas of supercritical hydrogen.
I'm sure in the planet, well, in space, you can find all sorts of extraordinary forms of matter that we can't find on Earth. I mean, beginning with neutron stars, which are just mass of neutrons. And I think I'm sure that on these gaseous planets, even on Venus, which has a very high concentrations of carbon dioxide in the atmosphere, it will be supercritical. But the atmosphere in Venus is quite hot. So even though the pressure is high, the CO2 will be a long way from its critical point. So it will be much more like the normal gas we know than a supercritical fluid, because it's only relatively close to the critical point that you get some of the attraction between the, if you like, the residual attraction between the molecules that you find in the liquid. And hydrogen, the critical point, I can't remember, is very low. And helium, it's even lower, it may be 20 degrees Kelvin. So ask me more questions.
Okay, another one from Ali. How is niobium phosphate an acid if it doesn't have H+? I think from a sort of Lewis School's point of view. There.
Oh,
sorry, Larry Bronsted. Sorry.
It does, because the thing is that it has OH groups on the surface.
And one more question from my feed here. Are there any times when research can become frustrating or difficult?
Yes, 95% of the time. And the point is, I don't know how many of you have done fishing. And when you fish, you sit by the river or lake for hours and nothing much happens. But then when the fish bites, it's really exciting. And research is much the same. The things often go for months without working, and then there's some breakthrough. This evening, about an hour before the lecture, one of my students phoned, and he suddenly made a reaction that was only giving 10% of product, has suddenly got up to 43% of product. And if it's right, and it may well be that he's deluding himself and it's not working, this will be really quite a big breakthrough, and just what we're waiting for in that particular project.
Excellent. Have you got any more, Steve? I've got a couple here on this feed.
Okay.
So someone's asking, what has been the most challenging experiment that you have had to do in your chemistry career?
Well, the thing is that it's important to say that I, as a professor, or even before I was a professor, don't do many experiments, if any, myself, because my students or postdocs, those are people who've already got their doctorate but are working in research, do the experiments. I think probably the xylene oxidation was probably one of the most difficult experiments in terms of making sure that things didn't blow up, or I should say didn't blow up too often. But I think I'm not sure. I think one of the important things with doing research is that you have, it's a bit like playing chess. I'm a very bad chess player, but you have lots of possible moves in chess. And similarly, if you do an experiment and it works, there are all sorts of things you can do next. And it is thinking what is the cleverest, the best thing that you can do next. Cleverest in the sense that it'll give you the most information, which is one of the challenges. I should say that I've done several experiments where I've thought I've had a brilliant result, and it's turned out to be completely wrong. And perhaps the one I remember earliest in my doctorate, I was working by myself late at night in the lab, which we're not meant to do. And I shone a light on a frozen liquid containing my metal carbonyl, and it glowed bright blue. And the metal carbonyls were not meant to glow bright blue. And I got so excited I couldn't sleep all night. And the next morning I went back and I thought perhaps I should do a control experiment. and I froze the liquid without the metal carbonyl, and it glowed bright blue just the same. So it was nothing to do with it. But I'd had the excitement, so what the hell?
Excellent. So for going for the most challenging time, this links in. Someone's asking, what was the most exciting event or the most exciting or highlight in your career?
That's a very depressing question. It implies that it's behind me. I don't know.
So far, should we say, so far?
So, well, I don't know. I think scientists are a bit like journalists. If you ask a newspaper journalist which is their most exciting story, they'll say the one I'm working on at the moment. And chemists are a bit the same. The most exciting thing you're doing is the one that we're working on at the moment. And it may be that when it's over, it won't be as exciting as we think, but that, if you like, is what keeps you going. But I think I'm not sure what the highlight of my career is, and I don't have a slick answer to that. I'd say I enjoy most of the things. But I suppose one of the most important things that to come out of research is actually to train young people to do research, because nobody knows how important the work that I've done will have been in 20 or 30 years' time. I haven't discovered the neutron, I haven't discovered C60 or whatever. But on the other hand, I have trained lots of students who will be able to help society, as I said, to solve the challenges of the coming years.
Can I just say, Martyn, thank you very much for all the time you've put into this, for giving the lecture tonight, for answering all these questions. And also I can assure you that it was definitely not a boring time we've all had. I'm sure we've all learned things about research, and all the students, I'm sure, have learned a lot tonight. So thank you very much for all you've done, and thank you for doing it in this way, in this situation. So thank you very much, and thank you to everybody for attending this evening. So have a good evening, everybody, and keep safe, and we'll see you in 2 weeks' time. So thank you very much, everybody.
Thank you.